Hello viewers, welcome to EF. Today I would like to discuss about the proof of Rice's theorem. This is the fifth video of complexity theory. If you want to better understanding this video, please have a look at my previous videos where I already explained different kind of definition. So what is Rice's theorem? Rice's theorem says that with respect to recursive set, any non-trivial runtime property of an algorithm or program is undecidable, means any non-trivial property cannot be decidable algorithmically. So now uh, for this proof, what we will do, first we will assume that there is a algorithm that can decide any non-trivial property of a program. So let's see. Assume that there is a non-trivial property proof for which there is an algorithm that determines whether the input program P has the property or not. So here prop algorithm PROP Boolean prop algorithm will decide that program P should have the non-trivial property or not. We know that there is no algorithm, so inside of this program it is empty. We assume some boolean result and we will return the result. If the parameter returns 0, that means this program P does not have any non-trivial property, and if the parameter returns 1, this means that if the program returns 1 means program P has the property proof. So what is this actually means? So in this program we just assume that here we have an algorithm that will decide program P has the non-trivial property or not. It will return the boolean result. Since prop is a non-trivial property, so there would be at least one program that will satisfy the property and it will return yes, means the program has a property, non-trivial property, and that will be designed by a Turing machine TMQ without loss of generality if the program does not have any any non-trivial property or does not have accepted any input. That TMQ means Turing machine of program Q will be phi. Then means that means it is an empty set that does not have the non-trivial property. So what do you mean by loss of without loss of generality? It means that the empty set does not fulfill the property, but there is of course only true of half of the cases, because the empty set might have the property or might not have the property, but we are not actually considering the empty set. So the empty set does here the opposite, but here in this argument we just saying that the empty set is not taken. Now in the second step we will prove the contradiction. For that we would like to create another program q2. q2 is q2 is a boolean program that will take some input x, and we will call program P with some W input inside of it. Boolean uh, Q2 has a result variable that will return the result, and this result will return only program Q of X. What is returning? What it means, like we are calling here the halting problem program P with W input, and here the result is depending only the program Q what is doing with X input. So we know that just before I said that Q will decide if there is a non-trivial property, then program Q will satisfy and it will return yes. And if it does not accept any input, then TMQ is saying just fine and it will return no. So that the result in this this program, in the second program of Q2, will return, no matter what is happening with the program P with W input. What it means that if we do here the halting problem solution algorithm here, like there could be three situations. First, P will terminate with W input, and fine, we will ignore and we will go to the result where the result is depend on the program Q with X input, and we will just return it with output. Means if there is a non-trivial property, the result will say yes, and that will be the result for the Q2, and Q2 will also say yes. On the other hand, if P does not terminate with W input, then also fine, no matter what is the result of it will directly pointing to the program Q2, and if there is not accepted any input in Q, then TMQ will return the 5, and that will cause the cases of Q2 is no. Now there is another situation. What if P is infinite loop with W input? Then it will be infinite loop, and it will not accept with none input and always end up with an infinite loop. This is the three situation with P calling with W. Now, what is actually Q2 is doing? I have a program P terminate with W input, yes or no. Then Q2 will have such the property of Q, which I can determine with the property, non-trivial property with probe algorithm. So that's what here is doing, and that is the contradiction we find out here. What is that? Turing machine Q2 is designed to implement a decidable decision problem Q2, where probe Q2 is the algorithm that will decide. That is, the output is yes only if Q says yes when P terminates with W input, and Q2 has the non-trivial property. So see here, Turing machine Q2 is equals to TMQ if P terminates with W input, or phi or empty set if P does not terminate with W input. And also we can say prob Q2 is approximately like TMQ2, which is actually written yes or 1 if P terminates with W input, or 0 or no if P does not terminate with W input. Now the now the interesting part is here. We already know in our previous video, I already explained that there is no algorithm that can solve the halting problem. So if such a program we can do for pro, then we can also solve the halting problem. But it is already proven that it is not possible, and hence probe does not exist. And this is the contradiction that we are assuming. There is a probe algorithm and there is no halting problem solved. So we have the contradiction here. If I can do the Q2, I could also solve the halting problem. If we could do any algorithm for check non-trivial property algorithm, I can also solve the halting problem, which is the contradiction. Even we cannot solve anything. So that's all for the proof of Rice's theorem. We know that there is no algorithm that can solve the Rice's theorem like halting problem. Thank you for watching this video. I hope you will see my next video. Thank you again.